I want to welcome you to the Marston Exploration Theater. I'm Ramon Aerosmith. I'm the Deputy Director of SESE, so it's really nice to have everyone here tonight. We'd like to make sure to thank Susie Marston and her family and all of our SESE friends for making this event possible. And we're having a big push because today is Sun Devil Giving Day. So please, if you're feeling generous, support SESE, support ASU. And today is kind of a big day to do it until midnight. So you can go online, cc.asu.edu/giving, and make a contribution and support us. We'll really appreciate it. And there is, if some people may have the Sun Devil Rewards app, and it's possible to use our secret word for the night, stars, to earn 100 pitchforks. So it's a special feature of coming out tonight. So we're really fortunate to have a presentation from Associate Professor Judd Bowman tonight. Judd he has 2 bachelor's degrees, one in electrical engineering and one in physics from Washington University, St. Louis. Then he went to MIT, got a Ph.D. in physics, had a postdoc or 2, and then came to ASU in 2010. So he's been with us for some time and is really one of our shining stars or early reionized piece of light or something. So he's an experimental cosmologist interested in the formation of structure of the early universe, so stars, galaxies, black holes. Very exciting. And his current research focuses on the development and refinement of technologies that enable observational probes of the redshifted 21-centimeter line of neutral hydrogen gas. So this is really an exciting way of seeing back so far in time and deep into space. The other interesting thing about his work is that it has to be done in very radio-quiet places. So a lot of his work is done in Western Australia and the outback and other remote locations. Along with being a great researcher, Judd's a significant teacher in SESE and also has important education and outreach activities. He's been working on a project called Dr. Discovery, which is an app that lets people explore and learn about science in general. So recently, and obviously a lot of people are quite interested, Judd's recent work has received a lot of press, and so we're really lucky to have him be able to answer some of your big questions you may have. So thanks to Judd, and let's hear about the dawn of a new era in cosmology. Thank you.
Okay, well, thanks, Ramon, for the great introduction, and thank you guys all for coming out. I'm really, really excited to be here and to talk to you about this topic today. This is a topic that's been at the core of my research since I was just a budding little graduate student all those years ago, and I think it's a really great story, so I hope we have a good time. What we're going to do today is go on a journey. We're going to go on actually 2 journeys. We're going to journey around the world as I talk to you a little bit about our efforts to make the new types of measurements we've been working on, and we're going to go through a journey in time, back in cosmic time towards the beginning of the universe. So that's the plan. Okay. So first of all, let's make sure we have some agreement on what is cosmology. And so it's kind of a funny word. It's one of those words that sounds like a few other things in the English language that involves hair and things like that sometimes. But cosmology is really simple. It's really just the study of the universe on the biggest scales. So here's a definition from NASA. Cosmology is the scientific study of the large-scale properties of the universe as a whole. We endeavor to use the scientific method to understand the origin, evolution, and fate of the universe. So that's what cosmologists do, and that's at the heart of what we're going to talk about today. So I have one of my favorite quotes in science. It's from a physicist, Ernest Rutherford, and he says, and I'm really sorry because I know there's not just physicists in the audience. He says, all science is either physics or stamp collecting. And so that's horribly untrue characterization of science. But it's a funny quote, and in this context, it actually is a little bit meaningful because we're not interested particularly in any one star or any one galaxy. We're interested in the collective properties of all stars, all galaxies, and how they're changing with time. So in that sense, we're not collecting individual stamps here. But I hesitate to use that quote, but I think it does give some perspective. Okay, so what are we looking at over here on the right? So this is a simulation of the universe, and the little sort of bright spots are places where there are galaxies and many galaxies and clusters of galaxies. And it's just been evolving here as I was speaking. And hopefully you were just kind of keeping a little eye on it, and you could see that there's some patterns in this simulation. First, as it was going through time, things were coming together. If you were looking at it a little bit earlier on, you maybe saw a bit of a honeycomb structure to it. And so there are patterns in the universe that we can see and observe that are on structures, on sizes that are bigger than galaxies, sizes that are much bigger than anything we think about on a regular basis. So let's start by talking about the history of the universe. So here's a timeline of the universe. The Big Bang is on the left, and today we're not quite on the full right. They stop. Here's today over here, and for some reason they kind of had this morbid sort of perspective, and they wanted to end this particular plot with the death of life on Earth. But we can forget about that. That's billions of years in the future. That's not our concern at the moment. Let's just talk about the history of the universe up until now. So the universe started. The observable universe began about 13.8 billion years ago. So that's billion with a B. And that's this boundary right here. And what happened was, we don't know what happened at the very beginning, but at some point we know that all of the observable universe that we can see today, if we look around us today with our telescopes and peer all around, we can see roughly a region of universe that spanned up to 90 billion light years in some sense. And so we know that entire area, that entire volume, fit in roughly something the diameter of a millimeter at this threshold right here. And this is really kind of when we begin talking about the universe as observational cosmologists. So everything, the entire universe today was about 1 millimeter in scale back then. And we don't, at the moment, I'm not going to discuss what happened in the fraction of a second before that size of universe showed up. That's too much for our talk today. We're going to talk about all the things that happened after it. And so what happened after it? Well, the universe was just extremely energetic, very dense energy place at that time. But as it expanded, it's been expanding ever since. And as it expanded, it cooled. And eventually, particles could start to form. And so we got, after a few minutes, we started to see things like the nuclei of atoms. And this is really like just protons, right? That's what's in the nucleus of an atom. So things like protons and neutrons. And that was, the universe just kept expanding and cooling, and there was these protons and neutrons floating around, and electrons. And eventually, after about 380,000 years, those protons and electrons were able to stay together and form atoms. And so that forms really sort of the beginning of the universe in sort of human-like terms than things that we think of, because the universe was mostly a gas. It was essentially a gas at that time, a gas of atoms. And then in some sense, it got really boring for a long time. It got boring in that it took from 380,000 years after the Big Bang to of order 100 million years before there was a thing in the universe. There was just gas, but there were no stars and planets and galaxies. And it took over 100 million years for gravity to act on this gas, and little density changes from one place to another. There's a little bit more gas over here than over there. And so those places that were a little bit more dense over 100 million years eventually collapsed and formed the first stars. And that's when things get exciting. Then you have stars, then you have galaxies, you have light, and you have eventually planets and everything that we know and love about the universe today. Okay, and so the universe keeps on going, and that basic picture, stars and galaxies and planets are evolving. We'll talk a little bit about some key phases in there. About 9.5 billion years after the Big Bang is when our own solar system forms. That's about 4.5 billion years ago. A few 500 million years after that, we get life forming on Earth, and then the rest is sort of the history of Earth that you can read about and look at and see in the geologic record. So that's the connection in the big picture. Okay. So how do we know about the universe when it was much younger than it is now? And the answer is one of these just fabulous, fortunate sort of features of the universe, which is that time moves, or that light moves at a constant speed, at a fixed speed. And so telescopes are effectively time machines. When we look far, far away, we're seeing something as it was a long time ago because it took a long time for the light from that object to get to us. So here's an example, and this is what astronomy is really built on, right? Astronomy is really built on this principle. So if we are here on Earth, and we look at the moon, we're seeing the moon as it was about 1.3 seconds ago. It takes light 1.3 seconds to go from the moon to Earth. If we look at, when the sunlight that we see all day long, that sunlight, if you looked at the sun, which don't look at the sun with your eyes, but if you looked at it with appropriate filtering, you would see the sun as it was 8 minutes prior to when you're actually looking at it. The nearest star other than our sun, it takes light over 4 years to get here. A globular cluster of stars takes light over 25,000. This is just an example of one in our own galaxy. It takes light over 25,000 years to get to us. Similar amount of time for light from the center of our galaxy to get to us, roughly. So we see lots of our galaxy as it was tens or hundreds of thousands of years ago. We want to look at the nearest neighbor galaxy, Andromeda, the nearest neighboring galaxy that's roughly similar to our own. It takes light over 2.5 million years to get here. So this is how we see back in time. We can't go back in time, but we can see back in time. All right, so this effect isn't just an astronomical effect. This is happening right here in this room right now, too, right? All of you in the back, you're seeing me as I was about 50 nanoseconds ago from your perspective. So light goes about 1 foot in a nanosecond. So we just don't notice, right? We don't notice nanoseconds. That's a billionth of a second. We're not going to notice. Okay. So how far back have we seen? How far away have we been able to look? We've been able to see with the Hubble Space Telescope all the way to something where the light took 13.4 billion years to get to us. So you remember that the age of the universe is 13.8 billion years. So that gets us back to within 400 million years of the dawn of the universe. And that's what it looked like. So this is the Hubble Ultra Deep Field, and this is one little nascent galaxy, little smudge in it, galaxy GNZ11. And for the astronomers, Z is redshift. So that tells you what redshift it's at. So in a very real sense, okay, look, we all know that time is money, right? And in astronomy, this is completely true too, because it's not cheap to get time on big telescopes. But in astronomy, time is also distance. So that's the take-home message. Time is distance. So here we go. So time is distance, distance is time, and here we are. We're going to be at the center of our own universe, right? And so astronomers really see the universe as a giant sphere. And it's like living in the inside of an onion, or for the geologists here, it's like living on the inside of a geode. Is that right? Like those are the hollow rocks, right, with the minerals in them? Okay. So we're in the middle, and we can just look out. And we look out, we see galaxies and things that go out. And as we look out, we're looking back in time. And so really, there's just really no distinction to us. The farther away we look, the farther back in time. And so in a very real sense, just by looking farther away, we can look and see galaxies that were in the universe at earlier and earlier times in the universe. So putting this back into scale again here, so now the age of the universe is 0 out here on the edge of the sphere. This is as far away as we can hope to see. And the age of the universe is actually, now it's 13.78, so we now tend to round to 8 on the end. Okay, so putting that Hubble farthest galaxy into perspective, it gets us back here to this time that was just several hundred million years after the Big Bang. So think of all the layers in an onion, and you're just looking back through cosmic time as you look through all those layers. Now, why do we want to see earlier and earlier in the history of the universe, right? Why do we want to see it? Well, let's start with a little more perspective. We've actually seen the afterglow of the Big Bang, right? Some of you may have heard of the cosmic microwave background. It's the most fabulously successful observational signal in cosmology. A lot of what we know about the history of the universe comes from seeing actual light that was the afterglow of the Big Bang. So all of that radiation and energy, right as the universe was starting to form matter, we see the leftover light. Then we see nothing, because the Hubble telescope gives us our earliest galaxy where we actually see something. So we have this big period in here where there's nothing. And then we see lots and lots of galaxies after that. So really, if you think about the universe kind of like a human being or like a person, we have like the baby picture, right? We have the very first image of what it's like warm and fuzzy and cuddly, and it just kind of sits there kind of wiggling around and doesn't do much, right? And then we miss all this exciting stuff like its first steps and its first words and whatever other things little kids do. And then the Hubble shows up and we start to see like the universe as galaxies are like adolescents and teenagers kind of emerging and making their presence felt on the world stage, maybe like college students, right? They're lots of mergers happening, lots of energy. They're really changing everything around them. And then you go through, you just start to see those galaxies going through life. And about 3.5 billion years after the Big Bang, those galaxies have reached peak productivity. They're the best office workers they're going to be. They're making stars at the fastest rate they can. And then for the next 10 billion years, they start to slow down. You know, they're kind of like us in middle age now, and they're still doing good work, but they're slowing down. And that's kind of where we're at today, right? That's like the history of the universe as a person. And so we want to look back and back and back because we're missing these key times. Like you wouldn't want to, if you just saw a teenager and you wanted to understand how they got to be the way they are, you would definitely want to have seen like their childhood, right? You'd want to see that first step, especially if you're the parent. You want to see those early stars and how they got to be there. So that's our goal. And so how are we going to do it? So the Hubble Space Telescope has basically reached the end of its line. It's not going to see really galaxies much farther than this. And there's folks here at ASU that have been working on pushing it back as far as they can and seeing some of these early galaxies. And it's about as far as it's going to go. NASA's building a new space telescope, the James Webb Space Telescope. And it hopes to go to this next layer of the onion and get to the first galaxies. But will it ever see the first stars? And the answer is almost certainly no. And there's a couple of reasons for that. First, the farther away you look, the harder it is to see things, right? Things are fainter when they're far away. So it just gets harder and harder to see light from galaxies and stars when they're really far away. And the other reason is there just aren't very many stars, right? If you're talking about the first star, there's just not a lot of stuff out there to make light in those really early times. So we're going to do our best, and we're going to see the earliest things we can. But it would be actually really cool if we could study this time without having to look at starlight directly, right? Every telescope you probably think of is looking at starlight, maybe collectively from a galaxy or something like that. But it's essentially looking at light from stars. But if you this picture is real. I like this one because it's really nice. You see this fog and this haze here. This is actually really nice because it reminds us that at these early times, the universe was mostly hydrogen atoms, and it was a gas of those atoms. And it wasn't, you get far enough back and there weren't even any stars there, and it was only that gas of atoms. And so we can actually hope that we can build a telescope to see that gas instead of see the stars. And we're lucky in that these stars, stars are big energetic things. They leave their fingerprints on the gas when they form. And so we're going to go looking indirectly for these stars by looking for their fingerprints on the gas that was in the early universe. So, the hydrogen atom. That gas was mostly hydrogen, is mostly hydrogen at that time. So we're going to go looking for hydrogen. Here's a hydrogen atom. It's got a proton and electron. It's the simplest atom on the periodic table. Positive charge and a negative charge. And it's a great atom. It's the astronomer's favorite atom because it's pretty much it is the most common atom in the universe. And it does great things. It can absorb ultraviolet light. It can absorb visible light. It can emit those types of light. And it can absorb radio waves. And so we're going to go after the radio waves. So here goes the atom. I learned how to do PowerPoint animations today. So why do we want to see the first stars, and why are we going to look at hydrogen? So we already talked about it, but this is the periodic table of all of the elements, or at least most of the elements. And it's showing you by color coding, all these different colors on here, where those elements come from in the universe. So if you look at this, most of these things, merging neutron stars, dying low mass stars, exploding massive stars, exploding white dwarf stars, they didn't fit it on. Cosmic ray fission, that's like stars dying and making energetic particles and spewing them into the galaxies. And then the Big Bang, right? What we call nucleosynthesis, the elements that were made from the Big Bang. So if you look up here and you see like, everything on this table is made in stars, 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 and stars. There's really only two things out there that were around, right? The hydrogen and the helium, and there was a tiny, tiny, tiny little bit of lithium, and one or two other types of atoms, but not enough. So A is really, if we want to understand how we got here, like I'm not made entirely of hydrogen and helium, you guys aren't either. If we want to understand how we got here, looking for the first stars is going to tell us when the universe started making the ingredients of life and how it started going about it, right? And we have to go and use these other elements that were around to help us get a handle on that. Okay, so the universe was 75% hydrogen and 25% helium when the first stars were forming. Okay, so that's the introduction. So let's recap. Our goal in cosmology is to study the large-scale evolution of the universe. And in particular, we really are focused right now on understanding this missing link where we haven't seen how the very first structures in the universe get formed. We can't actually see those structures, the stars themselves, and so we're going to go looking for their fingerprints in the hydrogen gas around them. And we're going to use the fact that hydrogen gas can absorb and emit radio waves to do it. So here is a wonderful artist illustration of the first stars in the universe made for us by the National Science Foundation, who funds our research. And these little filaments are representing the hydrogen gas that was around them, that they formed from. And the idea here is it's showing the signal that we're going to go out and look. It's showing how it's made. So in the background, the kind of, is it reddish? This kind of reddish glow in the background is the afterglow of the Big Bang. The stars are making ultraviolet light, like the stuff that gives you a sunburn. And they're affecting all of this hydrogen gas that was in the universe at that time. And effectively, the stars, with their ultraviolet light that they're making, are priming the pump. They're putting this gas into a particular state that makes it easy for the gas to absorb the background radio waves from the afterglow of the Big Bang. So what we expect to see is a slight reduction in the amount of light, the afterglow of the Big Bang light reaching us once the first stars form. And that's what we're going to look for. So great, we know what we want to see. We just need to go out and get ourselves a telescope and go look for it. So does anyone recognize these telescopes here? Yeah, this is Kitt Peak, right? So we're in Arizona. We're here in our own state is home to some of the best best telescopes in the world. And this is just a nice example of them. A lot of astronomers come to Arizona to work with these telescopes. We cannot use a single one of these telescopes for this project. It's just the biggest travesty of my professional career that I came here and I've never even been to Kitt Peak. It's embarrassing to admit. They're just completely wrong for what we're trying to do. First of all, they're mostly optical telescopes, so they're mostly able to see visible and near-infrared light, and that's not going to help us for radio astronomy. So we need a radio telescope, and you guys might recognize some of these radio telescopes. Does anyone recognize the big one on the left? This is Parkes in Australia. There's a wonderful movie called The Dish. That's a famous movie in Australia that this telescope is like the star of the movie. I really recommend it. And I think just not just radio astronomers would like that movie. I think you guys would also. This is the Atacama Large Millimeter Array in Chile. And how about the one in the bottom? You guys recognize that one? Yeah, the Very Large Array in New Mexico. These are our fabulous world-class telescopes, absolutely wonderful, amazing science. Again, fundamentally wrong for what we're trying to do. All of these telescopes, the bigger a telescope is, and the bigger the dish is of the telescope, essentially the smaller the part of the sky that it looks at. All of these telescopes are designed to look at very small parts of skies, like individual galaxies of the sky. There's only one sky. Like individual galaxies on there, and study them in extreme detail. We're trying to look for a signal that was everywhere, and that is actually really hard to see if you drill in and look really into one tiny part. You really want to look over a big chunk of sky. So we can't use them. And there's one other reason we can't use them, and it's because the signal we're looking for is very, very faint compared to all of the other radio emission from our own Milky Way galaxy. So if you had radio eyeballs, and you could see the sky in radio waves, and then you made it into false color. So these colors are just falsely applied. They correspond to strength. Red is a lot of radio emission, and blue is less. This is what our Milky Way galaxy would look like. And what you'll note here is that there is blue. There's emission radio emission from our own galaxy everywhere on the sky. And it's very, very bright at the wavelengths that the part of the spectrum we're interested in. And the current telescopes, even if we could kind of finesse the part of the sky they look at and make them work, they're really not set up to find a very tiny signal against this extremely bright background. They take advantage of the fact that the things they're looking for are also pretty bright, and they kind of sit on top of this. But when you look over a big chunk of sky at once, you don't really get that ability to separate other galaxies from our own galaxy. So there are a couple of problems with existing telescopes. And that led us, starting about 20 years ago as a community, to start building our own, to design and build our own telescopes. So here's a telescope I've worked with quite a bit called the Murchison Wide Field Array, and it's in Western Australia. And you can see this telescope looks nothing like the other telescopes on the previous screen. These are all antennas, kind of these little spidery looking guys. We call them bow tie dipoles, bow tie antennas. And they see, each of these antennas basically sees the entire sky that's overhead. So it's very different than a big dish that looks at a very small part of the sky. Because the signal we're looking for is quite faint, and because this telescope actually wants to make maps of that signal and little tiny changes in it from one place to another, it needs many, many, many antennas to have enough sensitivity to see it. So we've been spending 13 years now on this particular project, designing and building and operating this array. It's very, very hard. It still has not seen any of this cosmological signal. It's a very big challenge, and we'll come back to this at the end of the talk a little bit. Because the project I really want to talk about today is this much simpler project in a sense. This is EDGES, the experiment to detect the global epoch of reionization signature. We just call it EDGES. And we decided, if it's so hard to make thousands of antennas do what we want, why don't we just boil the problem down to one? All right, let's just start with one antenna and go after the signal in a little bit different way, but try to just know and love that one antenna the best we can and get it to be the perfect antenna, the best antenna in all the world. And so that's what we've been spending 12 years now doing. Not always the one, we've had different antennas over that time. So what I'm going to tell you about for a lot of the rest of the talk is these days the work of several people, and here they are. This is Alan Rogers. He and I started the project back when I was a grad student at MIT, and he's been at Haystack Observatory, which is run by MIT for many, many years. Raul Monsalve was a postdoc, so he had a Ph.D. and he came to do research with us here at ASU for a number of years. He's now at the University of Colorado. Two grad students here in the audience today, Nivedita Mahesh, who is our current Ph.D. student, and Tom Mosden, who graduated in December with his Ph.D. So this is the core of the team who did the work that we'll be talking about. We've also had a number of students, undergraduate students here involved. And so since 2010, this is kind of our crew. Just to kind of name them, we have Jose and Brianna over here, and Hamdi and Sarah, and Lauren and Callie, and our newest addition is Leroy, who's been building all of our latest hardware for us. And so it's great. These are wonderful, all wonderful. Hamdi, we're lucky on EDGES. We have two geniuses who have worked on the project. One is Hamdi Mani, who is just absolutely, who came to us as a student, and we've kept him on. He works with several of us in our radio instrumentation labs. The other genius on the project is Alan Rogers. Both of these guys are just absolutely just out of this world in what they can do with radio instrumentation. But all of these students, Jose has gone on to work at IBM Watson, Brianna's at General Dynamics. We kept Hamdi here. Sarah went on to a fast management track at Raytheon, and these are still current active students. And the bottom is a student named Delani Seal, and he worked with Alan for a summer at MIT. So it's just an amazing bunch that we're able to work with here. So there are recent kind of heart of EDGES, but I want to start by giving you a bit of a perspective on how a project like this gets started. And I think in science, sometimes we take this for granted, but I think it's wonderful to talk about because sometimes things come about in a way that maybe aren't quite what you would expect. So this project got started, I was a grad student at MIT, it was about 2005, and I had been spending my thesis working on modeling the MWA, that other telescope with all the antennas, and trying to predict what it would see and how well it would do. And then my advisor, Jackie Hewitt, on the top right corner up there, said, you've really just been doing stuff like like simulations. Like you should get your hands on some real data and get some real experience, like real life experience before you graduate. I was like, oh, that sounds good. That's a good idea. And I was about halfway through my PhD, and we were like, we really could use a good project that could be done in the last couple of years of a PhD thesis timescale. And we got lucky because right about that time, one of our colleagues came through town, and he had gotten really excited by basically by this paper here. Can the reionization epoch be detected as a global signature in the cosmic microwave background? And this is basically saying you didn't have to build an entire array of antennas like that MWA telescope. You could build just the one antenna and go after this signal in a much simpler way. And that got us, we're like, that's the sort of thing you could do in 2 years in a PhD project. Let's give that a try. All we need is a really smart radio instrumentalist. Let's go call Alan. And it turns out he had also been reading about this and gotten really excited. So the paper was a few years earlier, but we didn't realize it. It took us a few years to find it. And I didn't know, of course, until after the fact that one of the main authors on this paper is our very own here at ASU, Roger Windhorst. And I hadn't met him yet, didn't know of his amazing work, but I think it's just one of those kind of funny coincidences that happens that you come and you find out now he's one of my close colleagues. So I think it's a really kind of neat way to get going. That's how we got started. So, all right, we're going to start an experiment, and we want to build a telescope that can go see this radio signal. First thing we need to do is where do we tune our telescope, right? What frequency do we need to look at? Fortunately, Roger and the other authors of that paper had told us where to go look. They said basically, go tune your telescope right into the middle of the FM radio station band. And if you know anything about astronomers, it's that we don't like bright lights, and if you've ever met a radio astronomer, we don't like things that transmit. And so this is like the worst thing you could tell. And it's not just the FM radio band, because the actual range where we're looking for this signal spans from 50 megahertz to 200 megahertz. And if there's any kind of gurus out there, you know that there's TV stations in this band, there's satellite communications. If you're a pilot and you fly an airplane, you've turned into plenty of beacons and you've used your radio at 120 megahertz. It's just a really crummy band to try to go see the astronomical sky in. But we have no choice. That's the band, and so that's where we tune. And the reason is, for us, not only is time money and time is distance, but time is frequency for this type of astronomy. And so you can literally tune your FM radio band, and for the cosmological signal that we're looking at, you can tune through cosmic time. So if you think about you're on your radio, and you're tuning between stations and you hear static, right? And people still do that? Does everybody just have like hopping radios now? But back in the day when you could tune the knob, when you're in between stations, you hear that static. Mostly what you're hearing is the noise from our own Milky Way galaxy, but some tiny percent of that is the afterglow of the Big Bang. And we're going to go looking for a tiny little dip, a tiny little bit of reduction in that Big Bang signal. All right. So on your way home tonight, feel free to tune through 100 million years of cosmic time. I find this really easy to keep in mind, actually, because if you think about the radio dial, like if you go looking for modern music like hip hop and rock, it tends to be up here on this side of the radio dial. And when you go looking for like classical music, it tends to be down here. So it was very convenient. I don't know why that is. Okay, so we're going to go build an instrument, and we need to start testing it to see if it works. And so here's a tiny little antenna. You'll see it more in a few more plots. I was living in Boston. Haystack Observatory is right up here on the northern part of Massachusetts. We couldn't test it in a city because of all these FM radio stations and things. And so we went looking around on this webpage called FM Fool, which tells you basically how strong radio stations should be for any place in the country. And we saw that this place up here in Maine looked pretty good. There are not very many radio stations up there. And so we would drive up in the Haystack SUV and power our little tiny instrument off of the car battery and put our antenna out and do some tests. And we did this a lot. I spent a better part of a year as a grad student going up and down to West Forks, Maine. We were there in the summer. We were there in the winter. We were there so much that the snowmobilers just started driving right around us. They didn't care. We had to deal with the snow. One of the reasons I didn't stay in Boston my whole life. But there's lots of local attention, right? The locals were really curious about what we were doing. And so that was great. That was really nice. Someone to keep you companion. Eventually, we needed to get a little bit more serious and look for a place where the radio stations were even quiet or weaker. So do you guys, anybody recognize, so we took a little handheld antenna, and when you're out driving around the western part of the United States, you get kind of punchy, and so we called this guy Sir Spindley. And you had to hold it with some attitude and give it appropriate deference. Otherwise, you just look like an alien hunting kind of person on the side of the road. This made it science. So this is out obviously not too far from Area 51 in that particular photo. So again, we had found some sites by looking on this FM Fool webpage, and that's what led us to drive all around out in this part for about a week or several days and up into the Great Basin Range. One way you can block radio stations. So okay, here's a map of the United States, and this is showing us all the radio stations and how far they propagate. And so we were looking for a quiet spot. And so eventually we wised up and asked these people to make this map for us, and we found that there's this hole up here, so we went up there. And so that's Southeast Oregon, and it's this place called Catlow Valley, and there's this National Wildlife Refuge for antelopes right up there. A really beautiful spot, and we drove all around, and there's kind of mountains all around it, and it blocks a lot of radio transmitters. There's the antelopes. Here we are. Here's us with our rental car this time, and here's Alan putting out our antenna. And we're just checking it out, trying to see where can we not hear radio stations through our antenna. It's really pretty, it's not a hard thing to do. You can do the first pass just by having your car radio on. But to be more sensitive, we put our own antenna. And I was just looking back at this data, pulling up this slide, and I realized this was the town dump for a town called French Glen up there. And so it was a really glamorous time when we were looking for a good spot. The problem was none of them were good enough. And so because we've been working on this Murchison Wide Field Array project, we knew that Australia had some really good sites. And that, in fact, the Australian government was working on building a radio telescope facility out here in Western Australia at a station called Bullardy. It's like a giant ranch about the size of Rhode Island, basically the size of that star, essentially the size of the ranch. And so we knew that site was really good, and we realized we were going to have to start using that site. To make it even better, the Australian government was putting in legislation that restricted the use of radio transmitters near it. So like, hey, that's a win. Like, someone's not going to show up and start broadcasting something that we don't want. So why is it so good out there? It's so good because nobody lives out there, and so it's just not economical to put radio transmitters out there. So we took advantage of that. That entire station, that's a 1,000 square mile station, had a family of 4 living on it. So a family of 5, but one had gone off to school. So you can work out that population density. It's a very small number. So we went out there in 2006 and put our experiment out there, and it was really good. This is my favorite photo of all time, summarizing science, because it's like here's our instrument is lit up and glowing as we study the mysteries of the universe, and here's Alan, this wise scientist, just like divining the mysteries of the universe right there on the spot. And if you know Alan, this is a characteristic, thoughtful pose of Alan. So, but we got great data and it went well. It was a good first start. It was encouraging. So we retooled a little bit and we came back. It took a few years and made our experiment better. And we came back. Now the station that was on a neighboring ranch. Now we're actually on the official ranch. And the Australian government had started putting some equipment out there. They had some trailers with power provided by solar power, and so we were able to take advantage of that. And we deployed our experiment again. So here's our little antenna, and there's a cable that runs back to this trailer. Here's the antenna blown up. It comes up to about your knee. That's a trash bag just to keep water out of it. And this is about the size of a shoebox under there. And this is our amplifiers and our radio receiver. And this is the computer that takes all the data. And we stuffed stuff in the computer just so it would take up less space. So a bunch of electronics we just jammed in there and glued and kind of bolted and epoxied in. And then when you're out on site, this is about the size of like a dorm refrigerator, and it's all metal enclosure called a Faraday cage, essentially, and it keeps your own electronics from emitting radio waves. And so we had to stuff our computers, and the solar power equipment was stuffed in there. And then we observed for a little while, and it was good. At least it got off to a good start. So I wanted to take a slight detour for a moment and talk about convenience versus portability in this type of astronomy. The very first people that detected hydrogen, and it was detected astronomically, the radio signal from hydrogen, was this group working out of Harvard, and these guys had it thought out, man. Like they were like, dude, you know what would be really convenient if we just hang an antenna out of our window and do some awesome astronomy. And so this is literally their office building on the Harvard campus, and this thing is called a waveguide. It's just a big old horn antenna, basically. Unfortunately, we couldn't do that because of the FM radio stations, so we had to build ours to be portable. We built our experiment to be portable, and so we put it in a bicycle shipping container, like for the airplanes. take your bike on a plane, and a suitcase. And I bring this up only because it came in handy. On that trip I just showed you in 2009 where we had deployed our instrument and things were going great, a few days later, we had to pack it all up. And so here we are. This is my wife, Cassie, who's done a lot of our field work with me. And we had it conveniently all packed up, and here it is. We're wheeling it across the outback in our suitcase. And have you guys ever seen the movie Spaceballs? So you know there was not an industrial-sized hairdryer in there, but it looks like it. And the reason this was really convenient is because it had flooded in the intervening time. You know, you're out in the desert, it doesn't rain, right? It's not supposed to rain in the desert. But when it rains, it pours, and the whole place had flooded. And locally, the guy that runs the ranch, Mark Helene, was like the greatest guy in the world. He has an airplane, because when you have a ranch the size of a small state, of course you have an airplane. And he came and he flew us out there so we could pack up our experiment, stuff it all in the little luggage compartment of his plane, fly it back to his homestead where we were staying, which is about 25 miles away, and then just run it out on the homestead until the water all ran away and we could get back to work. So here's what it looks like. You can see the shiny, this is all the water on the roadway, on and off all of 25 miles. It just completely flooded out. So portability was great at that particular moment. Okay, so I love some of the accompaniments that we've had out in our deployments. So here was our edges doing precision cosmology. Here were some onlookers. These were goats. One of the scariest moments of my life was there was a little hill. This picture is being taken from a little hill. And we stayed out overnight out here a few times, and the goats would congregate up on the top of the hill in the morning, and it would look like this scene from the apocalypse with like 50 goats looking over the hill at you. But we were brave and we stuck it out. Most of the time, the sort of company that we had out on site and have always is flies by the hundreds. This is Hamdy Manny being brave. You can see we start wearing fly nets and things like that. But they're attracted to the moisture. You know, it's really dry, and they come anywhere there's moisture. They really want to crawl up in your ears and nose and things. So if you're sweating, there they come. There's cuter guys that come around. Sometimes the paparazzi's out there. I don't really understand how they find us out there. But this is an actual film crew from the ABC, the Australian broadcast company. And they were out filming on the Murchison Wide Field Array, and we were doing a little work on that while we were out there. So over the years, we kept getting better. You can see how much nicer and fancier our antenna looks. Our ground, we put this mesh under the ground, underneath it, to make it look only at the sky. And then we get photobombed. So we can't help it. I guess we just attract attention. Sometimes it gets to be a little bit overwhelming. These are little baby frogs, little less than an inch long. And at the homestead where you stay, they live in the sewer system. And they're actually a really good thing, because when they're around, it means there are no snakes. And being Australia, you really don't want to find a snake, because it's probably poisonous. So we actually kind of like having them around. But Hamdy was not a fan. And he had actually devised this. I don't know if you can read it. This is his frog cleaning, lesson 1 in frog cleaning. They enter your room through 3 sources, access points. Number 1 is the toilet. Number 2 was the shower, and number 3 was the sink. And he had devised, this is Hamdy doing a drawing of how you stuff up your toilet so the frogs don't crawl out of it. So you learn some interesting skills in the outback. Just to say, over the years, we also kept looking for other sites. Just, you never know, you might find something better around the corner, but we got much better at it. And we learned eventually just to strap our antenna to the car and just take our data as we drove down the highway, and then look at it after the fact. So we got pretty efficient. And of course, in Australia, this doesn't stand out at all. They're totally cool over there. They're like, pull up in a restaurant, fine, that's great, cool, you got an antenna on your car, whatever. And I just find this to be one of my favorite photographs, just of a very Australian sort of rural moment with a herd of sheep and actually it was a dog actually herding the sheep across the road in the back. It was really cool. Okay, but eventually we have to settle down and make a permanent home. And so in around 2014, we were working with the Australian government and their Commonwealth Scientific Industrial Research Organization, their version of the National Science Foundation. They run this site, and they were helping us to get a permanent installation out there. And so here we are as we finally settled in and made a permanent home. So the process, we had this little hut they had given us that we keep our electronics in. We had to move it. We got to help. We got to pull our own power and internet lines to it. This guy's Michael Ray, and he I thought I was a relatively practical guy because I build instruments and I thought I knew how to do things in the real world, unlike some physicists. I learned in the outback I know how to do nothing in the real world, and that this guy is like our hero who basically done everything for us. Here's Cassie again. She got to be the one that always stood down in the little pits because she was just a little bit smaller. It was a little bit easier for her to kind of crawl down in there. And here's her. So even after we pulled all of our own internet and power lines, we then had to pull, these are radio coax, like for your coax TV, like your TV cables, basically. So what our experiment uses. And this Cassie had to get down in the pit again, another pit, and pull those through. This is the only time she's ever gotten in one of these pits, because every other time she's been convinced that there's either spiders or snakes in them. And so I'm the one that sticks my head down in them. Then you have to build, this is basically a mirror so that our antenna looks up and not down, because as much as we love geology, we're only want to look up at the sky. The weather out there is basically like here, and so this is solid metal, and we were building this in the summer, and you literally couldn't touch it with your skin without singeing yourself. And so we had this like house insulation foam so we could sit down on it and do things. And just to prove the point, we boiled or cooked an egg. Nobody ate it, so it was okay. We forgot to put oil. You forget you should put oil underneath anything you're cooking on a metal surface. And we eventually got very smart, and we used this special paint called Goldstone No. 7. It's a white paint that reflects infrared and visible light, so you don't heat up. And so we painted our whole ground plane actually, so we could walk on it basically. And when you're going to go somewhere permanently, it's nice to know what's happening on a day-to-day basis. And so some of our undergrads here at ASU made us what they call the EMI, which stands for our electromagnetic interference low monitoring unit. So if you look at the three letters of that, the acronym is very fitting. EMU for EMU. And we put it out there, and we had a camera that looks up at the sky and can tell us if it's raining or what's happening, and also one that looks out at our experiment. So here again, you can see a rainy day, you get puddles on the ground. Our experiment's very sensitive to the environmental conditions. And then, once again, the locals like to see what we're up to. We never ended the building, okay? We built one antenna, we built another antenna. This is Cassie welding now. 1,800 welds to make one of these big metal meshes underneath. That's about 9 straight days of welding, about 9 hours a day. It's a lot of welding. We built another antenna that required another 1,800 welds. We got a little bit fancier, not good posture here on my part, but we were able just to kind of slide along on this little cart, and that we got faster. So there's our last antenna that we built, antenna low band number 2. So we have a total of 3 antennas out there right now. So what do we do with them, right? That was a lot. Like there, we spent years and years building this thing, and there was no science in all of that. There was very little science. But now we have science. And so what do we get when we turn on this instrument? Here's what we measure. Here's frequency, right? So here's, like on your radio, here's your radio dial right up in this part up here. And here's basically the temperature of the sky at those different frequencies in the spectrum. So how much radio power we're receiving at different frequencies. And this is actual data. This is what we see. This beautifully clean, I know what you're thinking. This is the most boring data I've ever seen in my life. It's just a curve. It doesn't have a wiggle, and we want to find wiggles, actually. We're looking for wiggles in this business. All of the wiggles in this data are tiny. They're teensy tiny. They're within the thickness of that line. So this line is 99.8% radio power from our Milky Way galaxy, which is caused by electrons moving almost at the speed of light, spiraling around magnetic fields in our galaxy. That's what makes the shape of that line. 0.2% of what's making up all of this power in here is the afterglow of the Big Bang in microwaves and radio waves. And what we're going to look for is a little tiny dip that's at the 0.03% level. Something so tiny you can't see it on this plot with your eye. So how are we going to do that? The only way we can have a prayer to do that is that we know what this big, bright curve should basically look like, because we know the physics that creates that signal. So we can model it and we can subtract it. And when we do it, we see this little teensy tiny dip. Now it looks big because I drew it, but if you look at the scale here, we're talking 0.2, 0.4 temperature units as opposed to like 5,000. Right? So that's what we see. That is the signal that we think is cosmological and coming from the early universe. So I have a sonification of it, but I think maybe I'll save it. If anyone really wants to hear it go, whoop, whoop, we can play it later afterwards. We just did it for fun to have something to listen to. So There's one catch with what we've seen, and that's that the signal we saw was twice as big as we expected, twice as big as any theorist predicted. And so we're trying to find a tiny little signal against a lot of other noise, and we want to know, did we do it right? There's a lot of ways you might do it wrong. And so what we did is we spent 2 years after we first saw that signal, and we did test after test after test to try to verify that it was real. And so this is a list of all the tests we did. And all we can say at the end of that is every single test we did, all the evidence we have is consistent with that signal really coming from the sky and not being some error in our instrument. We don't know, we haven't completely ruled that out, right? We're still working on it, and we're hoping other people will go out and put out similar instruments. But everything we've done so far says that even though it's not what we expected, it's consistent with a true cosmological signal. So what do we learn from it? Well, there's a few things we can learn. So first, it's not what we expected. It suggests there's some mystery lurking out there that is completely new to us. There's only 2 ways that we can really think of to get a signal that's bigger than we expected. One way is that all the gas in the early universe was colder than we thought, or that there's more radio waves out there than we thought. So they were absorbing some radio waves. If there were more of those radio waves, the signal would look bigger. So since we published our paper about 3 weeks ago, there have been about 15 other papers following up, proposing ideas on what might be causing this to be bigger than we expected. And they fall into really 2 categories. One category is that there could be some dark matter interactions happening in the early universe. So if you know about what makes up our universe, of all the energy and matter in the universe, 70% of it is something called dark energy that we know nothing about, that's making the universe expand faster and accelerate its expansion right now. 30% of what makes up the universe is matter. And of that matter, only 20% of it is normal matter, like atoms, like that we are made out of. The other 80% of the matter is something we don't understand, but we know it interacts by gravity. And so if you think about ways that that matter that interacts mostly with gravity, only by gravity, might possibly interact with normal matter, it can give you some ideas about how to get this signal that we're seeing. So there's a bunch of ideas that talk about how it might be dark matter doing this, which would be really cool if it's true, because we really want to know what dark matter is. The other cool idea is that there's stuff in the early universe making more radio waves than we thought. And one of the ideas that's been proposed there is that we need to talk about black holes real quickly. That there were black holes in the early universe, and they were spitting out radio waves. They absorb, they accrete matter, and as they accrete matter, they accelerate particles, and those accelerated particles will make radio emission. And if you get just the right sort of circumstances, you might imagine that could make our signal just right. So those are really cool ideas. And I imagine if we wait another 3 weeks, there'll be probably another dozen papers on some other ideas out there too. So we're just gonna have to wait and see what it could be. But what we can say at this point is that we know that by the timing of the signal, by the frequency of when it starts, that there had to be stars in the universe by 180 million years after the Big Bang. Otherwise, we don't think our signal would be there, because we need the stars for the signal to be there. And we know that the signal ended, the frequency that it ended at in the FM band is telling us that the gas got warm enough by 250 million years after the Big Bang that it was no longer able to absorb the radio waves. It actually would switch into emitting radio waves. And we're looking for that signal now. So those are the 2 things we can really say. And if you kind of take that and you apply what we know about galaxies today, the properties of galaxies today cannot explain really those times. And so we know that galaxies in the early universe must have been different then. We can infer that from this observation. They were different, and that's not too surprising because the stars were very different. And so the environments were different. So that's not horribly surprising, but it means you just can't easily extrapolate back. So what we want to do with this now, so just to wrap up here in the last few minutes, what we want to do now is, this was a detection experiment. And we're moving on into an era where we really want to quantify this signal and make maps of it. And remember, this is a signal where we can actually map an entire volume of the universe in 3 dimensions. Each frequency corresponds to a different time or a different distance. And so here's a simulation from a theorist that's showing the dark stuff is all the hydrogen gas, and the light in here is from early stars and galaxies. And you see how they're breaking through the gas, right? So as more stars and galaxies are forming, they're breaking through the gas with their light. And they're effectively turning this gas. They're taking the atoms and they're knocking the electrons off of the protons. They're turning the atoms into the gas into a plasma. And so this process is what's called reionization. And it's the last major event in the history of the universe where something happened to everything in the universe. And what we want to do is actually map that, like tomography, like of your brain. We want to map that era in the universe and just see how that unfolds from one time to another. And it's really, really valuable probe because embedded in that signal, you have the density of gas, so you know where there's a lot of gas and where there isn't a lot of gas in the universe. You have where there's galaxies and where there's stars, and you have what types of light those stars must be making in order to make that gas get ionized. And so if you want to say, how do we understand the early universe, you'd want to know where's their stuff, where is it turned into stars, and what have the stars done? And that's exactly what you get in that one observation. That's why we're so excited about the potential of it. Okay, so we don't want to watch those other YouTube videos. So what we're doing now is building this telescope, the Hydrogen Epoch of Reionization Array, HERA. It's in South Africa, excuse me, another place where there aren't very many radio transmitters. And several of us here at ASU are working on it, including Professor Danny Jacobs, who is leading the commissioning of this. So this telescope, we're going back to making kind of dishes. We're hanging our dipoles above them this time. And the idea is this is a very cheap way to go about it. It's made out of wire mesh and PVC, literally out of PVC. And telephone, these are telephone poles. Here there are 19. This was the status maybe 6 months or a year ago. At the moment, there's almost 60 of these dishes. And within a year, there are going to be over 300 of them out there. It's a phenomenal array. It's about 300 meters across, so 3 football fields in any one direction. So that's where we're headed. And this array, we think, will be the first one to be able to start mapping that signal that we just detected. So to end, in SESE, we don't ever end with the doable and what we're working on right now. We're really excited about where can you take this, where can it go in the future, and what's the potential for humanity. And so, to be honest, the best place to make this measurement is from the moon. Okay? It's the most radio quiet spot in the inner solar system. There's no radio transmitters on the moon. If you go on the far side of the moon, you're clean. Right? There's nothing there to get in your way. Right? And we didn't talk about it, but there's a layer of the Earth's ionosphere that actually starts to absorb radio waves and makes the sky wiggle around. It's very similar to optical observing, where you talk about seeing, but it happens for radio telescopes too. And we really want to avoid that as we get better and better. So here we are. We're just going to hold up the moon as the future of where we're headed. And we've been working on concepts. And so you could imagine taking our EDGES experiment and putting it in space. So EDGES in space is this concept called DARE. We've worked with the University of Colorado to build up this concept. And the idea is you go and you orbit the moon, and whenever you're on the far side of the moon, so the moon's between you and Earth, you go do your cosmology. That's easy. That's a good starting point. Where we really want to head is building arrays on the moon. This is a much, much harder problem. So you want to put arrays on the far side of the moon. So you got to land things on the surface of the moon. You want to put out hundreds or thousands of antennas. So you got to do it at extreme scale. You got to find ways to miniaturize, reduce the cost, reduce the volume, automate, maybe build things on the moon. And then go about this. We've been talking recently with folks at NASA who are working on what's called the Deep Space Gateway. And this is a station that NASA is working to put behind the moon in a kind of special orbit that more or less stays always behind the moon. And it's going to have a crew on it, people. And so we're working with them with ideas about how that could facilitate building an array, using it for communications to get data to and from our array on the moon. So that's where we're headed. That's the future. And so I just want to thank you all. We've come through a journey around the world and to the moon on this talk and back through cosmic time. Just to highlight that we saw the first evidence for starlight in the early universe. We think there's awesome new mysteries lurking out there. And really the future of cosmology, I think, is going to be this type of radio observation. It's where we're headed. So I've had a great time. I hope you guys have enjoyed it. Thank you very much. So I'm authorized to take some questions.
Judd, we're going to actually
Okay.
use microphones
Great.
because we're streaming, so we'll
Great,
do that.
there's a guy right here.
There's one over there and right up here.
Oh, I do. All right, so I'm an undergraduate here, and recently in my coursework, I've been working with Dr. Wenhorst and his project about like population 3 stars and whether you'd be able to see them or the imprints of them with the James Webb Space Telescope. So I was wondering, since I recently, like as you go really at higher redshifts, like their like size on the sky actually gets larger because due to the expansion of the universe. So like if these stars, like we know that they're quite large, but if they're far enough away, their angular size will be large enough. Is there any like way in the future, like even like 5, 10 decades from now, that we'd be able to see light from them? Because they're really bright, but they're
Yeah.
also spread out over a larger area. So that's kind of
Yeah, that's a great question. I mean, there's nothing completely fundamental limiting us from ever seeing a very early, like one of the very earliest stars. I think you would just need some really gigantic telescope, right? Some really gigantic infrared telescope. And so you're right. There's a few folks, Roger's group and Evan Scannapieco's group here, are looking at how we might see. So the earliest stars in the universe, the ones that formed out of only hydrogen and helium, we call them population 3 stars because we're astronomers and we like to do things backwards. So those types of stars, we might also get lucky and see them forming a little bit later. That if you had a little pocket of gas that never got enriched with other elements in it by stars around it and stayed only composed of hydrogen and helium, you might even see them a little bit more recent, right? And I know Roger's working on some of that. So we're hoping we can get lucky and see some of the same types of stars in the next decade. But if you really truly want to see the very earliest ones, I think it would be decades away. I think before we could. We're working here on SESE on building the giant Magellan telescope and getting involved with the new giant optical telescope here on the ground, and that's going to help. But I think it needs to go even beyond that if you want to see those very first stars.
So I understood that you had a baseline expectation of what you wanted or were hoping to be able to see, and then the readings turned out something different. How did you calculate your baseline? What were you expecting to see, and why was it? How did you figure it out?
That's a good question. So I've never actually calculated the baseline of what we should see. There's an entire group of people, we call them theorists, and they spend their careers calculating those kinds of things. So it's numerical simulations where you'd start with a model of how dense and how there are little different perturbations in density of gas in the early universe, and then you propagate gravity through there. And you add radiative physics so that kind of at certain times when places get dense enough, the model says, aha, a star must have formed here. And then you say, okay, I know what stars they should make light, and it should have ultraviolet and X-rays and optical. And so they propagate sort of these models where they build on all these layers of physics to it. And then they just let time run in the simulation. So they're the ones that calculate what the signal should look like. And in fact, they have, because it's so little is known about this era, they have many sort of variables in those models that they can, kind of adjust, and they can get us, and tell us, say, the first stars should have formed at 50 million years, or 100 million years, or 200 million years after the Big Bang, and just by kind of twiddling some knobs. And so they give us a range of expectations to look for, and that's why we go out and make the observation then, is that we can actually kind of pin it down to one particular case. Now, it's possible they didn't put all the right physics in their model, right? And that's why when we say what we see is twice as big as we expected, but it's not impossible. It's because there's other types of physics they just didn't think to put in. Maybe the dark matter, way they modeled dark matter wasn't right in their model, or it was neglecting some aspect. So that's an additional step that now that you have some data, they start to think more carefully too.
Just one more regarding the difference between the modeling of the hydrogen base and the dark matter base. Are you able to put them on top of each other to see what they look like?
Yeah. So we're able to, the theorists are able to combine the two effects into one model. And one of our colleagues has done that and made some prediction or different scenarios for us already. And we've been looking at fitting those to our data. Not quite ready to talk about, but yeah, you can absolutely. I mean, that's what they get excited by this kind of thing. And as soon as they realize maybe there's something they overlooked, they want to try to think of how to add more physics to their models, and then they'll, we get to kind of see what they give us. Yeah.
What would be the likely mass of these earliest stars?
Good
Is
question.
it just calculated? Can you calculate it, and also can you determine the mass at all from the data you're getting?
Right. Okay. So the mass of the earliest stars. So from theory, we expect them to be very massive stars, 10, 100, maybe even 100 times more massive than our own sun. And that's just because what they're forming out of, those ingredients, hydrogen and helium, leads to a different type of star. If they're massive, they're also very short-lived. Maybe just living 10, 50 million years, and our sun is going to live billions and billions of years, right? So we have an expectation that they're very different. the types of observations we're making, in principle, can start to tell us if those ideas about the early stars are right. At the moment, we're really just at the detection phase, and so we're not trying to analyze our data at that level of detail to be able to try to constrain what the stars were like. So as we go forward, that's absolutely where we're headed, though. This sort of observation and the mapping of all of this with Hera that we want to do in the coming years, which should tell us the sizes, the timings, what type of radiation they made, what they turned into when they died. We think a lot of these early stars turned into black holes and other things like neutron stars, really compact objects after they died. And those objects were responsible for making a lot of X-rays that then heated the gas in the universe. And so we'll be able to tell a lot of those details as we get more and more data. Play the noise. Is that good? Is there?
I do have one question when you're finished.
Yeah, go for it.
So you mentioned you're looking for wiggles in your graph, but mate, you're based in a country that has a very famous band called The Wiggles that do a lot of children's music. So I don't know if you kind of factor that into your expectations. But my actual question, I actually have a couple, but let me just distill it down to one.
Where are you?
I'm right in the back, right underneath
right
the
under the
projector.
bright light. Okay.
Sure. The size of your grid that you were doing your 1800 welds on was very like a non-standard shape. Is there a reason for that size, and how does it relate to how it reflects the signals you're seeing so you're not going into geography?
That's a great electrical engineering question. So all of that wire mesh that's under our antenna, you might have noticed it has kind of a pointy sawtooth edges on it. That actually helps. What we really want is an infinite surface of wire forever. That would be like an ideal antenna. But we can't do that, and so we have to make one that's finite in size, and it has to be within the bounds of how much Cassie is willing to weld. And the best way then to make it have the best properties is to put those zigzaggy edges on it, because it actually kind of reduces current on the edge of the antenna. So it kind of reduces the reflections from the edge of that ground plane. And so that actually, one of the biggest issues for us as an instrument is that our antenna, it's responsive to different parts of the sky more or less. And at different frequencies, it's responsive to some parts of the sky more than at other frequencies. And that's a really bad thing when there's all this other structure on the sky from our own Milky Way galaxy's emission. We want to minimize that as much as possible. So we want to try to make our antenna achromatic, right? Not changing with color, with frequency. And one of the ways we go about minimizing it is putting those little zigzags on the edge. That's a cool question.
I have one other one about a more system engineering question than electrical. What do you do with your data when you're running your little computer in a little Faraday cage? You have limited space inside your PC case, right?
Yeah, so okay.
Do you go run a collection on it every so often, or does it have a certain amount of data that you can only collect before you have to scrub it off onto another drive?
So one of the great things about doing such a simple experiment is we don't generate very much data. Our entire installation out there generates 4 gigabytes per day, which is nothing in the realm of big science these days. And there's an internet connection out there. So we just stream it back here to ASU every night. And so we don't really worry about filling up a hard drive or anything like that. Does that answer? Yeah. Okay, so we'll end with the whoop-de-doop. Okay. Oh, okay. Yeah.
Do you know what the shape of the Big Bang is? Is it roughly spherical? Is there any way to know that? And then once you know that, where are you looking to listen? Are you looking at the part that's expanding away, or what?
Okay. So first, what's the shape of the Big Bang? And this is something that's really one of the more challenging parts of thinking about the Big Bang. We don't really, and I didn't really help by saying the entire observable universe was condensed down to like a millimeter in diameter. But in essence, we don't know how far on that len, right? We don't know how actually big the universe might be, and it might not have a definite size. So really, when we're thinking about things, we're thinking about density, right? That at that time, all of the stuff in the universe was in that tiny cubic millimeter of space. So it's not really about thinking about the shape of the Big Bang or the shape of what was right after it, because we don't really have any idea if there's a boundary or not. But the density was so compacted down into something that high. And the second half was, where do we look? So, in that we live in this sphere that we can see out. We can look anywhere and see the signal. What we do in practice is look where the galaxy has its lowest radio emission, just kind of for obvious reasons. But one of our big tests to verify that what we see is likely actually from the sky was to look at multiple places on the sky and see that we got a signal that was consistent between all those spaces. So everywhere kind of beyond our local group of galaxies is moving away from us. So everything that most astronomers look at is moving away from us. And in this, we can look anywhere. All right, go for it. So this is a lot of hype for this. Okay, so here's the spectrum. You're going to see this little dot move across it, and there's going to be a tone that plays. One more time. Wow. Ramon wants one more.
All right, that's excellent. Let's thank Judd again. Woo! All right, well, thanks so much, everyone, for coming tonight. And don't forget, we have one more lecture this semester and our Earth and Space Open House featuring Dr. Nat Butler on April 13th. And that one's going to be Chasing Gravitational Waves. So another cool one. Don't forget, as you leave tonight, we've got some SESE brochures and postcards, and they'll also help you to also not forget about Sun Devil Giving Day. So thanks for supporting us and supporting future explorers. So thanks a lot and good night.